So a couple of objects there that said in the tactics box. If the force pulls on one end of the rope, the tension in the rope equals the magnitude of the pulling forces. If the two objects are connected by the rope, the tension is the same at both ends. That's the second thing. And if the rope passes over a pulley, we're going to assume that the tension is unaffected. So we'll see that later on here. That if this object pulls down with 10 newtons along this rope, then all the pulley does is it changes the direction of the force. Okay? So if this, although probably be more accurate to say, let's say this mass pulls down with 10 newtons, okay? Then that would mean that that tension is transmitted through that rope, and then that would be pulling up 10 newtons on this particular object over here. So all the pulleys really do is just change the direction of the force. It doesn't change the magnitude at all. Now, there was friction and all that other stuff, and if the rope was, reasonably heavy, then that would make a big difference. But we're assuming the ropes don't weigh anything, and there's no friction on the actual pulley. Okay? So, we're going to work through these problems. If you notice, there's no numbers on these, and that's fine, because what we're primarily concerned with is showing you how to set up these problems for your homework problems and quizzes and things like that. Then there will be the actual numbers, and all you got to do is plug those values in. Kevin, how's that glare?
Not the best.
All right, how about now? A little better? Okay. So the instructions say draw the free body diagram for each object, assume the existence of friction, unless I tell you otherwise. We're going to write Newton's second law for each object, and then we're going to identify anything that's the same, okay, such as the tension or anything that can be written as an equation, okay? So here you go. Let's deal with these objects. First, let's consider this small one right there. So what are the forces that are acting on that? Weight going down, normal going up, friction. Since we're pulling this, we would call this a system of blocks. Since we're pulling it here to the right, friction is going to act, we'll say friction 1, okay? Since we'll call this maybe object 1 and this object 2. And tension, you say? Tension 1. Looks pretty good. What about for object 2? Circle that. What are the forces acting on it? All right, hold on. I have here weight. James, what's another force acting on it? Normal force. Nancy, what's another force acting on it?
Friction.
Friction, which way, left or right?
Left.
I agree. We'll say friction 2. Benjay, what's another force acting on it? Tension, we'll say from the rope, which direction? To left, yeah. See, this, if you were this box right here, imagine you were being pulled along, okay? That other box, which is over here, is pulling you backwards from the tension on that rope. So that is different from the friction. So we'll say the tension 2 right there.
Is it usually greater or less than friction?
It just depends on the situation. Normally friction's kind of small.
Okay.
Kevin, any other forces?
Did you say the box is moving?
Yep. I've got a friction force here. And somebody's pulling the box. So that, I'm going to call this, call it force external, or force 1, or it looks like called force external. That's the actual hand which is doing all of this stuff.
So wait, but would there be like something attached to the box but they're pulling the left side and adding the different force to it also?
You're talking about like if they're pulling it with a rope. Okay, so yeah, if I don't have a rope here shown, it just says force external. But yeah, if there was a rope, then we could maybe call that tension 3. I'm just calling it force external because maybe they grabbed it and formed it like that. Okay, let's go ahead and write Newton's second law for each one of these. Now, which Newton's second law is easy to write for these?
Oh, why?
The y is easy. Okay, so summation of forces in the y direction, normal going up minus weight going down equals mass times acceleration in the y direction. So, yep, there's no acceleration in the y direction. So actually, normal equals weight. And if we wanted to, we could substitute in, Ivan, you remember the formula for weight?
Mass times gravity.
Mass times gravity. Okay, so if we wanted to, we could continue this all the way through. Normal is mass times gravity. Let's just finish up talking about box number 1. Summation of forces in the x direction. Tension 1, just going to the right. Minus friction. I'll put Fk since we'll assume that the boxes are moving, so kinetic friction equals mass times acceleration in the x direction. We've got all kinds of space here, so we'll carry this other one off to another sheet of paper. So, anything do we know about friction force, kinetic friction force? Yeah, hopefully it is less than tension. There is a formula for friction force, mu n. So tension 1 minus mu k times n. Might as well carry this all the way through. And what's the normal force?
mg.
mg. So I have tension 1 minus mu k times mg equals mass times acceleration in the x direction. Sort of carrying this all the way through. This is our last section, so it's a good sort of review for everything we talked about in this chapter.
So the normal force is mg.
In this case, it is equal to mg because there's only two forces acting on it, weight and normal. And I should clarify that. I've got it as little m. Maybe I could call it m1 if we wanted to separate. I'll follow this convention. When we talk about the mass over here, I'll use a capital M. Okay, so let's deal with box number 2, summation of forces. We'll do the easy one first. In the y direction. Normal, now I might need to identify that this normal is different from this normal. So maybe I'll write normal 2 minus weight 2 equals mass times acceleration. In fact, we're going to be fully consistent here. Mass, I'm going to write big M because it's the mass of this object times the acceleration in the y direction. Is object 2 accelerating in the y direction? No, so that actually whole term goes to 0. So same thing, we have normal 2 equals weight 2. So normal 2 equals big mass, so big M, times gravity. Summation of forces in the x direction. Now, this is going to be pretty large here. That'll get us started. Give us some values here for the summation of forces in the x direction.
Force external minus tension 2 minus friction 2.
Equals?
Mass acceleration in the x direction.
Yep. And I'm going to put big M for that mass. Now that I'm thinking about it, I've got acceleration in the x direction, but I've got an acceleration in the x direction for object 2 and acceleration in the x direction of object 1. So if I wanted to, I could put a little subscript 2 right here. Y'all see what I'm saying?
Yeah.
Okay? And I could go down here and say mass times acceleration in the x direction of 1, 1, 1, you know, put a little 1 subscript down there.
Should their acceleration be the same?
Yes, they will be. Thank you. So I bring that up only to then say what Gracie said. This got her. Okay, thanks. So, I wasn't going to mention that till the very end of this, but we can put it as a little side note. The acceleration in the x direction of object 1 equals the acceleration in the x direction of object 2. Now I want you to think about that and think, why is that the case? And there's one more thing that's the same.
Friction.
All right, first question. Anybody want to give it a shot? Why are those two accelerations the same?
They're attached.
Yeah, they're attached. Think of it like this. Here they go. Moving together, right? So if big mass 1 here, or mass 2, I guess the big one, is traveling at 5, you know, accelerating at 5 meters per second, then this one over here also has to be accelerating at 5 meters per second because they're attached. So, absolutely. So as soon as I put that AX1 equals AX2, I can, from here on, I'm just going to write it as AX, and everyone will know that's the case. Okay. There is one other thing that is the same. I might as well mark it here right now. Anybody want, there's something that's going on with object 2 that is the same as a force present over here in object 1. Anybody want to make a guess?
Considering the x direction, or does not?
Friction.
Friction is not the same.
Tension.
Tension is the same. Friction is not the same because friction force is based on the mass and the gravity. Technically, it's the normal force, which depends on the mass completely in this case, and that coefficient of kinetic friction. So, yeah, tension 1, however, equals tension 2. That's both sides of Newton's third law. Come on, what can I do for you?
Density.
Right in front of you.
Oh, hello.
Tension 1 and tension 2 are actually two sides of Newton's second law. If, you know, object 1 is pulling on object 2 with a force of 5 newtons, and object 2 is pulling on, you know, object 1 with a force of 5 newtons. So that tension is both sides of the same rope, so to speak here. So tension 1 equals tension 2. So I could replace that T1 with just T in this case. So I'll say force external minus tension minus friction force 2. Are you okay if we just write mu times big M G? Because we determined that it's mu N and the normal force is big mg. So equals mass times acceleration in the x direction. So we call that's equation 2. Equation 1 is tension minus mu k little m g equals little m a x. That's two equations. And that's almost as far as we can really get in this situation. Because I'm not telling you the coefficient of kinetic friction, I'm not telling you their masses, I'm not telling you the external force. But look at this, if I did, for instance, if I told you the external force and I told you their masses, look at all those different things that you know. If I also maybe told you you know what G is. You know what, if I told you another common thing to give in these problems is the coefficient of kinetic friction. So that would give you this and this. At that point, what are the only things that you don't know?
Tension and acceleration.
Tension and acceleration, okay? So if you remember from your math classes, if you have two unknowns, it is possible to solve that if you have two equations. All right? One thing you could do is you could solve this entire formula for tension. You could solve this entire formula for tension and then set them equal to each other and then just go through and figure out what the acceleration happens to be. Or you could solve this one for acceleration, solve this one for acceleration, and go through that. All sorts of different things that you can do. One last thing, since we're analyzing this one to death here, okay? It is possible to treat this entire object as one system, or rather, excuse me, this entire system as one object. So think of it like this. Or one giant object of mass little m plus big M with F external pulling on it, weight 3 going down, normal 3 going up, and the friction force F K3 going to the left. So it would be possible to just treat this entire object, this entire system, both of those, as just one big object. That doesn't really sound, very, proper. I mean, because you've got two objects there, how can you just sort of combine all of them? Well, just think of it like this. At some level, even at like the microscopic level, what object 2 is literally, there's a particle here, and there's a particle here, and there's a bond in between them that's functioning like a rope. And next to that one, there's another bond in between it that's functioning like a rope. See what I'm saying? And so you could, what we call object 2 is literally billions and billions and far more than that of actually little particles that are attached by ropes, which are the molecular bonds. Okay? So we're just grouping all of them together. So it's just not much of a step to take two objects and group them together, and then you might be able to write a free body diagram for that whole thing altogether. Okay, but enough of that. So let's go ahead and look at a pulley problem. You might need to write this on another sheet of paper if that took up a whole lot. Kevin, question.
Will the tension between the first box and the second box, will that always be the same as the?
Absolutely, and let me have you walk up in here to demonstrate that for me, okay? So, well, maybe I should get a rope. We'll use this for right now. You pretend this is a rope. Let's use your headphone wire. Okay, how about your lanyard?
There's a string right here.
Oh, there is. Okay.
He knows
Almost
what I
right,
love
that
that.
All right, can we? All right, here we go. All right, so every single time, if I'm pulling with 10 newtons, what do you feel? Yeah, it feels 10 newtons, okay? All right, but I'm also feeling, I pull this way on you, okay? Then that force gets transmitted all the way along this, okay? So you're feeling that pull, okay? But since I'm pulling, I'm also feeling you pull. It's an equal and opposite thing. It's the same thing as a push. If I push, you're pushing also back on me. It just happens that you accelerate because I have my feet firmly planted on the ground. Okay? All right? So same thing here. I'm pulling, you're pulling, and I'm pulling you, you're pulling me. It's always going to be equal and opposite. What we could do is we could get those force sensors and we could hook them up together. We could pull one and the other, and have the other one pull, and they'd read the same thing. Maybe I'll do that for you on Tuesday. All right, that's good. All right, let's look at the pulley problem here. Pulley around here. Here you go. I'll have to take a pulley to play with, pass it around here. Oh, you want a string too?
Yeah.
feels cold right there.
Oh my gosh.
Oh, I'm so good.
There's some strings in case you. Alright, so after you get that, you can pass that around. While they're playing with the toys there, the rest of us will work on this. So, we've got mass 1 and mass 2, that's great. Free body diagram, Nancy, on mass 1. What are the forces acting on it?
Wait.
I'll say weight 1, and?
Do we use that?
No, good question. No normal because there's no surface that it's touching. Just the rope which is pulling on it, which we use the letter T for tension.
So hold the string.
And I'll call that tension 1.
Would it be the same?
Is it the same or smaller?
Good
The same, because it's only changing the direction.
Well, I
But
haven't
the
told
other
you
one
what's
is
going on.
bigger.
If I was holding both of these up like this, and then all of a sudden I were to pull my hands away, what do you think would happen?
It would bother the
The heavy one would fall, and this one would rise, correct? Alright, Brooke, you with us?
Yes, sir.
So if I were to pull my hands away, what would the heavy one would fall and the light one would rise. So because the heavy one would fall, then we would assume in the light one is accelerating upward, that the tension on the light one is
Oh wait, on the light one or
on the light one, on M1.
It's greater.
Greater, okay, so yeah, I agree. The tension one
It's between.
is greater than the weight one. Let's go ahead and circle object 2. Jasmine,
Yeah.
what are the forces acting on object 2 there? Let's call it weight 2.
Okay.
And
Tension
tension 2. Greater than or smaller than or equal to weight 2.
Smaller.
Why smaller?
Because it's heavy. I get it, I just don't get words.
That's fine, you're good. As I pull my hand away, just tell me what's going to be happening with mass 2.
The one that your fingers are by is gonna fall.
Okay, so that means that there's got to be more force pulling down than pulling up.
Right.
So therefore, the tension has to be smaller than weight 2.
Like I get it, I just can't tell you why.
Yeah, okay. In fact, definitely looks smaller. As a happy coincidence, I've done something else with this diagram which also matches a very real situation. Talk to me about the tension 1 and tension 2. They are the same. The same thing was going on with myself and Kevin here a minute ago. All right, Kevin,
Yes.
bring that string.
It's behind you.
Bring a pulley. Emily, I need you up here as well. You're tall.
Oh, I thought he was talking to me and I was like, I'm not
All
tall.
right. Okay, see if we can do this. Emily, you're gonna stand over here with your back to the wall. All right, here we go. All right, so observe, class. Just hold it. Just hold this just like this, so it doesn't even. The pulley's not even doing anything. All right, Kevin, go ahead and pull it. Oh, he's pulling me. I'm pulling him as well. Okay, so he's pulling. All right, great. No big difference, right? Just it's a rope. Now, what's the only thing different? She's gonna hold it up, Kevin. We're gonna. That's fine. It's Kevin. Bring your hand over there. Okay, great. So now, Kevin, pull. Try to pull it in such.
It'll still come down.
Alright, oh, he's pulling it, and now I'm pulling it. Alright, see, now you're pulling, and you're feeling 10 newtons, and I'm feeling 10 newtons. There's a little bit of friction there. You can't feel the fighting it, right? Okay, so what's the only thing different in this situation versus this situation?
The weight.
Not the weight. It's more of like an angle thing. It's more of the direction, okay? Before he was pulling that way, and I was getting pulled that way, and I was pulling this way, and he was getting pulled this way. But now he's pulling down, and I'm getting pulled up. Or I'm pulling down, and he's getting pulled up. It's just the direction that's changed. The pulley just changes the direction of the force. Does that make sense?
So instead of having
Yeah.
X component, you have a Y component.
Yeah, exactly. Now we'll try it, Keep it kind of low right there. Alright? What if I just kind of put it at an angle? See, now I'm just pulling at this angle, if he's pulling at that angle. It's the same, keep going. I pull, you know, he feels me being pulled, now you go ahead. Now, just go straight out across. It's still the same, you know, it's still the same exact thing. It's just at a different, it's just in a different direction. I'm still pulling the rope is still accelerating, the rope is still transmitting. I'm pulling at 20 newtons, and that 20 newtons is pulling on this particle, and that 20 newtons is pulling on this particle, and that 20 newtons is pulling on this particle, on this particle, and this particle, and each one of them just, it's transmitted all the way down the line, until all the way over there at Kevin's hand, the last particle that's next to his hand pulls, okay, 20 newtons, and so therefore that pulls his hand at 20 newtons. Do you see what I'm saying? It's just transmitted. The only thing that's different is the direction. Go ahead, Kevin, have some fun with the pulley. Pulleys are great. Okay. In fact, you can take that and send that around. It's pretty good rope for that. So, Miranda, I think you said that, right? Tension 1 equals tension 2?
How do we get that? Yeah.
Absolutely. Okay. And kind of like we have over here, what about the acceleration, right? The acceleration. The magnitude of the acceleration is the same,
The direction is off.
but the direction is opposite. So we would say the acceleration of object 1, which is going up, okay, that's in the positive direction, is equal to negative the acceleration of object 2. And if we wanted to be extremely technical, we would say object 1 in the y direction, object 2 in the y direction. Are y'all okay? I'm not going to write Newton's second law in the x direction since there's absolutely no x motion at all. Just going to be concerned with y direction. So for object 1, summation of forces for object 1 in the y direction is tension going up minus weight 1 going down equals mass, so mass of object 1 times the acceleration of object 1 in the y direction. So we could write that as tension minus mass 1 g equals mass 1 acceleration 1 in the y direction. I particularly don't like this double subscript nonsense, so I'm just going to say that acceleration 1 in the y direction is just a acceleration. Okay, so t1 minus m1g equals m1a. Emily Velasquez, could you get us started on the summation of forces for object 2 in the y direction?
Would it still be tension minus weight?
And I'm going to say weight 2.
Okay,
Keep going.
equals mass 2
Mm-hmm.
times acceleration 2. What, in this case, you could just say negative acceleration y, right?
Yeah, okay. I'll put acceleration 2 in the y direction for right here. And then my next step, when I substitute everything in, so mass 2 times gravity, mass 2, and then I'll just write negative a like you were suggesting. So this is a good first equation. This right here is a good second equation. And then, you know, if I gave you the masses, then you could plug those numbers in and you would have 2 equations, 2 unknowns. You could solve for one of them. Would you like to go through that process? Let's go ahead and do that real quickly. We need mass 2 to be larger than mass 1. So mass 2, 10 kilograms. Mass 1,
5.
let's make it 4, just so that, because 5 is when you get half, stuff like that, so it's a little less than half, 4 kilograms. So we'll just go through the process of solving the 2 equations, 2 unknowns. You did it in Algebra 1, you did it in Algebra 2. Now you're going to get to do it in AP Physics. So, tension minus 4 times, instead of saying 9.8, let's play like this, the AP test. And we're going to say G is approximately 10 meters per second squared. So 4 times 10 equals mass, which is 4 times acceleration. So T minus 40 equals 4A. There's my first equation. My second equation, T minus mass 2, 10 times 10 equals 10 times negative A. So T minus 100 equals negative 10A. I have enough information, I can solve for everything. I can solve for the tension, I can solve for the acceleration. What I said before, in terms of how to solve 2 equations, 2 unknowns, you've got lots of opportunities. You could, if you wanted to, you could solve each of these for an equation and then graph them, find them where they intersect. You could do substitution. I could say, solve this for t equals, and then take that value and substitute it in to the other one. Do y'all remember substitution? That's a method. But in all honesty, one of the easiest ways, I think, is just to solve this equation for t and this equation for t, and then just set them equal to each other. Okay? So this equation, solve for t, is going to be t equals 4a plus 40. That's like a smiley face right there. And then down here I have t equals negative 10a plus 100, smiley face. I also kind of wrote them vertically. You know, another way besides graphing and substitution is elimination. If you remember that, you have all those techniques and stuff like that. But in this case, I'm just going to set smiley face equal to smiley face. So 4a plus 40 equals negative 10a plus 100. I'll add 10a to both sides. 14a equals equals 60.
Okay.
Yeah. I like it. A
60 or 14, which equals
4.3 meters per second squared.
And now that we have this, we can just plug it into my tension.
Exactly. Let's go ahead and do that real quick. Tension equals, I'm not even going to. So I'm going to take 4 times 4.3 plus 40.
times 40?
Yeah.
It's 172. Wait, hold on. 4.3 times 40.
Nope.
Times 4.
Look.
Oh, times 4, sorry.
So it should be like 60 something maybe.
Plus 40.
50, 60, 70 newtons, somewhere in there.
57.2.
57.2
Shut up, really.
newtons. So what I'm trying to show you is that what we've done here, this analysis is good for lots of different problems. They're just, at some point, they're just going to give you the actual numbers, okay? I think it's best, personal opinion here, if you set everything up with the variables first, and then you just plug in the numbers at the very end. So what we've done for our made-up problem, we have determined that mass 1, that smaller one, is accelerating upward at 4.3 meters per second squared, and that mass 2 is accelerating downward at 4.3 meters per second squared, and they're both feeling a tension. They're being pulled at 57.2 newtons. Ivan, I've got a question for you. We're saying that this object 2 is falling at 4.3 meters per second squared. Why isn't it falling, since it's, you know, there's nothing underneath it, why is it not falling at 9.8 meters per second squared?
Because of the tension is pulling it up.
The tension is pulling it up, and so it's not in free fall. It doesn't just have gravity, it also has tension. Does that make sense? That's why we're seeing a number here. And we already said earlier, I think it was over here, that the acceleration of object 2 is negative the acceleration of object 1. That's why it's going down. Does that make sense? So,
If we were to plug in the acceleration into the second formula, the negative, it wouldn't be negative 4.3.
plug it into this one right here.
Yes. Oh, never mind, because that's negative.
Because it's gonna have, it has a this one has the negative built in right there. Yes.
So if we're just writing it down, if it asks us for the acceleration of the box 1 and the box 2, for box 1 you'd say 4.3, but for box 2 you'd say negative 4.3.
That is correct. Yes.
Wait.
I'll repeat what she said. She said, if the question was asking, what's the acceleration of box 1?
You would say negative.
Well, box 1 is this one, and it's going upwards, and so that's a positive, and we declared that whatever A we get, that's going to be acceleration of box 1 in the y direction. And box 2, acceleration is negative of that answer, which makes sense because it's going down. Okay? I'm trying to find the most interesting equation of them all. Some of these on the back are just sort of fancy. I think the most interesting, honestly, is this thing right here. We're not gonna do the ramp one. That one's, well, I mean, ooh, yeah, let's do the ramp one.
Yeah, but they are happy.
Because the ramp one is exactly like this one, but it's at an angle. Yeah, let's do the ramp one. Not that one, this one right here.
We're gonna do all of them.
Nah, we don't need to do all of them. Okay. Theta, don't you love that? Yeah, okay, let's just. Theta. Let's circle mass 1. Okay? Alright, just call it out to me here, folks. What are the forces acting on mass 1? Normal. Now remember, normal is perpendicular like that. Okay? So for this one, I'm going to tilt the axis I've got normal 1. Keep going. What else do I have? Weight. Now normally weight is going straight down, but we are going to resolve that into part of the weight going down the ramp, and then the other part into the ramp. So this is weight 1 into the ramp this is in the y direction, but it's not what you would normally think. So it's weight 1 cosine theta, and over here we have weight 1 sine theta. We don't have a lot of indication whether this, which one's bigger. Just, let's say mass 2 is bigger than mass 1, okay? So if that's the case, what's going to be happening with this system? Friction. We'll say mass 2 is pulling downward, and so this one, mass 1 will be moving upward. That's not a guarantee. There could be enough friction to fight it, but we'll just say that it's right now the velocity is in that direction. So since object 1 is moving to the right, the friction force is moving to the left. Kinetic friction there. Are there any other forces acting on object 1? Tension. Tension 1. That's the hard one, believe it or not. What about object 2?
Just tension and weight.
Just tension and weight. Weight 2. Tension 2. Now, I said that object 2 is
The lighter one?
the heavier one.
Oh.
So the since object 1 has a velocity going up here, object 2 has the velocity going down. So I probably should make the tension a little bit shorter here than. Are there any of these quantities that are the same?
Tension.
Tension 1 equals tension 2. That's right. Anything else? Acceleration. Acceleration of object 1. Now I'm determining that this is in the positive direction, and it makes the most sense that for an object traveling downwards, that's in the negative direction. So once again, the acceleration of object 1 in the y direction is negative the acceleration of object 2 in the y direction. It's essentially just the same thing as you saw before. Only difference is object 1, hold on. Object 1 is accelerating in the x direction, right?
Oh no.
So object 1 in the x direction, his acceleration, is equal to the acceleration in the y direction of object 2, negative. Does that make sense?
So we don't have to. Does that, I don't know where I was going with that number.
Or worse?
It's,
Or is it the same as?
it really doesn't make any difference. It's just, I mean, this object 1 over here, it has no acceleration in the y direction. Okay, so that normal, so that just, who really cares about that? And this guy's not going horizontally. It just means that when I write my equations, Newton's second law in the x direction of this guy is tension minus the friction force minus the weight force, weight 1 sine theta equals its mass times acceleration in the x direction. And that acceleration in the x direction is exactly the same as object 2's acceleration in the y direction. Tension minus weight equals mass 2 acceleration in the y direction. Negative, yeah. But that's all I want you to really see from this one, is that this one's moving in the x direction, but if it's accelerating at 5 meters per second squared, that means this one's falling at 5 meters per second squared. And you can set up those two equations and go down that. This whole chapter we talked about friction force, tension, Newton's second law. On Tuesday we plan on having a lab. I will say it.
Don't say that word.
I have a nice lab on Tuesday. So Wednesday, 6-1 and 6-2. Have those read. Have a great 3-day weekend. NHS meeting at 12:30.
Where, in here?
In here. Always.